Hi, I'm Thijs de Vrije. I work at the Swiss Feather Labs, and in this short movie, I'm going to give you some insights on passive cooling technologies that can be used for smallholder farmers. Now, what will I talk about? Many different types of options are available actually. You have evaporative coolings, cold rooms and devices. You can also do this with spraying and misting. We have underground cooling systems, night ventilation, radiative cooling, high altitude cold storage, and cooling with natural made ice, snow, or cold water. Here you see some of the depictions of the technologies I just mentioned, which can be viable. These are some artistic images, just that you have an idea. Very important is a little bit that you're aware of the options available and that you choose the right one for your use case. So why do these passive cooling technologies would work? Well, actually, the idea you should have is that we use lower temperatures or cold energy to cool down fresh fruit and vegetables by removing some of the heat. And if we want to see which technologies are available to us, then we have to think about where do we have cold energy available in our surroundings that we can actually use in a passive way to remove heat from the fruit or keep it cool for a certain amount of time. And these are, we can do this in many different ways. I will talk about most of those. You can actually make use of shade so that heat is not exposing your build structure or the fruit even, which you try to cool or keep cool. You can also evaporate water, because in order to evaporate water from liquid to vapor, then you actually can extract heat from the environment. You can also look at temperatures below ground. They're often cooler than the temperatures above ground. Also, nighttime temperatures are often, air temperatures are often colder, and the sky is colder also during the night in many different regions in the world, by which you can also use radiative cooling. We often have lower temperatures at the high altitude, and of course, if snow and ice or cold water would be available, then we can also make use of this. So it's really to think for your use case, which cold energy do I have to my proximity during which time of the day, and how can I leverage that? So you have to think about this. In your case, not all of these technologies are available for a certain location in the world. So there are many different types of technologies, but very few of them are marketed by companies. So you have to be aware of this. So often passive cooling are homemade solutions. That's why there is not so much material available on these as well. Now, why and how do they work? I showed this image also in my previous movies. So what we actually try to do with passive cooling systems is try to remove as much heat exposure to the fruit in our built enclosure which we have. So this is, for example, heat by conduction, convection, long and short wave radiation, or internal heat gains, which we get from equipment which we installed inside our cold storage room. You also, of course, have the field heat, which is in the fruit and vegetables before they actually enter the cooling enclosure. Now, as I mentioned before, we have different ways, different passive cooling systems which we can deploy, and they all work on one of these, let's say, heat transfer mechanisms. So they try to mitigate one of these heat transfer mechanisms. A typical example which you see here is if you want to reduce shortwave radiation to our built enclosure, we provide shade. That's a typical thing. If we want to, let's say, reduce the air temperature outside, we could, for example, use high altitude cooling, so placing the cold store at a higher altitude. So these are typical examples of these passive cooling systems and how they would work. Let's first tackle evaporative coolers, cooling rooms, for example. Here you see a charcoal cooling room, two types of charcoal cooling rooms. How does evaporative cooling work? Well, as I mentioned in the previous movie, you actually wet a porous material. Then if air moves through this porous material, which can, for example, be charcoal or evaporative cooling pad, then due to the fact that you have liquid going from liquid to vapor, you need energy, and this energy is extracted from the air, by which you actually cool down the air that moves through this porous material. That's how evaporative cooling works. You have different types of evaporative coolers. You can have, for example, typical charcoal cooling rooms, which are rather well known. You also see a smaller scale charcoal cooler there on the right side. You can also have a brick sand cooler, which you see on the image on the left side. We developed ourselves charcoal cooling blankets. They work in the same principle, that you actually have charcoal which is wetted, and due to the evaporation and airflow going through this charcoal blanket, you actually get cooling. A very promising and well-known technology would be clay pot and pot coolers. They're used around the world as well, smaller scale than these big charcoal coolers, but they work actually very fine, as you see in the picture in the middle. Here you see an overview of a lot of work being done in, let's say, evaporative cooling, which we looked at. And then you see on the left side a typical temperature drop in many different studies that have been looked at. And on the right side, the reduction in weight loss for different types of products. What we see actually is that you can drop the temperature in the left figure by about roughly 5 to max 15 degrees. By evaporative cooling, you can reduce the weight loss and thus also the shelf life. You can increase that significantly. For different types of products, a lot of tomatoes and carrots have been tested, for example. So there's an added benefit of reducing the temperature. At the same time, you also humidify the air through this evaporative cooling process. So there is some potential. There are some boundaries, of course, with respect to temperature reduction. Here you see work we did just that you have an idea on the cooling of such a charcoal cooler. So this is a charcoal cooler room and also a charcoal cooling blanket. And then you see the ambient temperature on the top in black. And then you see that with our charcoal cooler or cooling blanket, we can actually drop the ambient temperature only during the day for a significant amount, for several degrees Celsius. So this helps to reduce the temperature inside the cooler, which can then, of course, increase the shelf life. On the other hand, you see that humidity is increased above, let's say, 80, close to 90%. So you also reduce moisture loss from the fruit and vegetables which you put inside compared to the ambient environment, where you see that the humidity often drops to, let's say, even 50%, for example. So that's how these evaporative coolers, let's say, work. You can have airflow, often it's by natural convection or by wind blowing through these evaporative coolers. And you can make these porous walls with different materials. Often charcoal is used in the sand brick coolers. As sand and brick are used, we use charcoal or sawdust or rice husk as well. So it depends a little bit on what you're looking at. You can drop the temperature 5 to 15 degrees, often not much lower, and it depends very strongly on the climate. So depending on the temperature and humidity of your environment, which of course varies during the day and with the seasons, you can actually, let's say, have a certain cooling performance, but very much dependent on the climate. On the other hand, you can humidify the air, which is good, as I mentioned, to reduce mass loss, but it's often only suitable for dry and hot environments. So you have to be aware of those. You cannot place them everywhere around the world. You can make small and large ones very low cost in-house. It depends on the scale you're looking at and on the materials you have available. To choose when and where you actually can deploy these technologies, we made, for example, a map of the world, but we can also zoom in online via this link to the specific location you're interested in, on how much you can actually reduce the temperature maximum in such, let's say, evaporative coolers. We did this for different types of months because, of course, the season depends or has a high impact on the temperature and humidity you get. Let's say. So you can have a look here if you're interested to see if evaporative cooling would work for the location and also the time in which you're interested to cool. Of course, this time often is linked to the harvest season because you want to cool close to the harvest season. So you have to make sure it makes sense. Don't place an evaporative cooler in a region or in a, let's say, place in time where it does not make sense, for example. That's a very important thing to note. As I mentioned, you have different types: charcoal cooler rooms, sand brick coolers, very small charcoal blankets. You also have swamp coolers, which work just with evaporation via a textile. And you have the well-known clay pot-in-pot or pot-in-dish coolers, which you see also here. Advantage, low cost. You don't need energy. You can already cool at the farm very easily, or at home even, and you have humidification and cooling at the same time. Very big disadvantage is that the cooling performance is really depending of the time during the day and also of the, let's say, the season you're deploying it in. So you have to be aware of this. Often this is a reason to, let's say, lose trust with farmers, because then they would see that it does not work so much. So you also need sufficient water to operate, and a very good training is essential. It's not so difficult, but it's essential that it's done in a good way. Otherwise, if it does not perform as you expect it to, then actually it will not be used in the future anymore. There are a lot of online, let's say, links which I put here, where there are some videos on how to build your own evaporative cooler. A very relevant company in this field, company foundation, is Coolvec Foundation. So they build a lot. They build a lot of hybrid evaporative coolers, and also have a lot of training materials available. You can also use spraying or misting to cool down. It works on the same principle. You would spray a little bit of water over the fruit, and then via airflow, this can be natural convection or wind, or you can even use fans. You can actually then evaporate the water which is on the fruit and then cool down the fruit in this way, or vegetables. Disadvantage is that, of course, you spray water on the fruit, so this can make that you have some microorganisms growing which you don't want to have, and you have to make sure that your water is, of course, clean. Very low cost, can be deployed everywhere, often at different scales. You can try to cool down tons of fruit or a small amount of fruit, but you need clean water. So you have to make sure you don't contaminate the fruit in this way, and it's rather difficult to have or to control the cooling process as such. So you have to do some close monitoring if it actually makes sense and it works for your purpose. Then underground cooling. Well, often the temperature of the soil, so at several meters below the surface, is cooler than the environment in some seasons. So in Europe, for example, this typical temperature would be 10 degrees if you go sufficiently deep, which is why a lot of cellars have been constructed in several parts of the world to preserve fruit and vegetables in a longer way. Root cellars, they're typically called, and so on. So we could try to make use of this system as well. This temperature is not only often colder during the summer, but also more constant. So this is kind of nice. You can build these, let's say, underground system in different sizes. That's kind of nice. You need to ventilate rather well, because you can have condensation problems. You can also have buildup of some gases, ethylene, for example, which you want to remove. And sometimes condensation occurs, so they have to drain that. The temperature reduction is very dependent on the location. So in several regions, the soil temperature is still rather high, because it's typical the soil temperature sufficiently deep below the surface equals roughly the annual mean air temperature. So you can easily look at what the annual mean air temperature is, and based on that estimate what your soil temperature would be. This is indeed around the equator often rather high still, but still lower than the temperatures you would have outside in summer there. So you can actually remove exposure to peak temperatures, which is very nice, but often these temperatures, if it's 25 degrees, is still too high to store fresh fruit and vegetables. So they will preserve better underground than they would do outside sometimes. On the other hand, these are suboptimal conditions for fruit or vegetables. Cost is really dependent on how large or small you make these things, and you can, if you have available, you can also use natural made, let's say, enclosures like caves and so on. We did not see this applied so much in low and middle income countries for, of course, many different reasons. Advantages are, as I mentioned, they're very easy to operate. You need to build them, and temperatures are rather constant. But you have this lower temperature limit, which is in some countries still rather high. And in some regions, you can even have flooding of these systems. You have to be aware of that. So apart from that, we can also try to cool with night ventilation. This is rather simple. When the temperatures drop during the evening, night, you would open ventilation openings. Then colder air can enter your cold storage room or your room which you actually want to preserve your fruit and vegetables in. And then these colder temperatures can be used throughout the night. In the morning, you would then close these openings again to avoid that hot air comes in and heats up your fruit again. So this is possible. You can use different types of ventilation. You can use, for example, wind. You can also use stack ventilation based on the buoyancy effect. You can even have fans producing airflow. Very important is that you insulate your structure a little bit, otherwise then the cold energy which you collected during the night is very fast dissipated back into the environment during the day. Important is that your nighttime temperatures are sufficiently low, because if they're not very, very low compared to the daytime temperatures, then the cooling effect will be rather low. So you have to be aware of that. And air cannot hold a lot of cold energy, so you need rather high volumes of air flowing through to be able to exchange enough heat and remove heat from the fruit. So you can combine it a lot with thermal storage. This is often this technology used in buildings as well, that you actually would store cold energy in rather heavy materials during the night, which can then actually dampen temperature fluctuations during the day. Very easy to operate and to implement at a very low cost, but they don't work in all climates. You have to control it in a good way, that you stop and start ventilation at the right time. And it really depends on the outside temperatures and also the ventilation rate. So you have to be aware of this. We can also cool during the night with radiative cooling. What does this mean? That if the sky gets colder during the night, which happens in a lot of regions, then actually due to the cold temperature of the sky, they can actually extract through radiation heat from, for example, your fruit directly, or from the cold store which you're looking at. You see on this image with this cabbage fruit, which is actually where they measure the temperature in the very early in the morning compared to a little bit later in the day. So this fruit has been cooled, amongst others, by radiation during the night, but also by lower nighttime temperatures. So you can extract a lot of heat just by radiative cooling, actually. So I explained already how this works. This is often works best for clear skies, because then the temperatures of the sky drop much longer and lower, and that you actually have a roof, let's say, which has a very large thermal emissivity. You can cool with radiative cooling a room. So if you paint or coat whatever structure with a high emissivity material, then they will radiate a lot to the environment, to the sky during the night. Preferably you have large surfaces. So if you compare to flat surface, if you have a dome surface, then you can actually have a much higher surface area radiating to the sky. This has been used, for example, in ice houses a lot in the past. So, but it really depends on how you design your facility. So you have to think about that. You can also directly cool the fruit when it's still outside. So if you would harvest in the morning, that you have cool fruit, which has been cooled by radiative cooling and by lower nighttime temperatures as such, so also by convection. So that's why it makes sense to harvest early in the morning or even in the night, because then you can actually have less field heat inside because you've removed some with radiative cooling. And this technology, radiative cooling, has even been used to produce ice. So natural made ice, because the nighttime temperatures of the sky dropped so much that you can produce thin layers of ice. They were harvested then in the morning, and then they're used for cooling fruit, vegetables, and other products as well. So that's another possibility. Very easy to deploy and so on. You need a large surface area. That's the downside a little bit, and it will also heat up during the day. So you have to be aware of that. So you have to actually have a good design of the entire structure. And of course, if you want to cool your fruit, let's say even after harvest outside, then you have to be aware that it can be prone to pests or wildlife or also theft. So it's less advised. It's better to cool your room directly. So that's that. Another thing we can also apply is using high altitude cold storage. So the higher you go in the environment, the colder temperatures become. So if you have a location available which you can access easily, where the temperatures are a little bit lower, it should not be snowing, as you see here, then you can use this to store fruit and vegetables because the temperatures are colder. So often works only for long-term storage, so will not transport all your fruit and vegetables there for, let's say, a few days or a week often. A typical example would be, let's say, apple fruit. You can preserve them for a longer time. So then a critical component is how you can transport fruit and vegetables to this location. Because if you lose a lot of fruit quality during transport because you have a bad road or a bad packaging to transport it in, then it could be even more disadvantageous to transport it all the way up. So you have to evaluate how much food loss would you have compared to not transporting it and selling it on the market. So that's very important. You also have to be aware that the cost as such for such a cold storage room, if you have it available, or storage room, is not necessarily so high, but you need to include the transport cost as well. So once you get it there, it's rather simple. You just have to transport it up and then collect it down. The disadvantages are it does not work for every fruit type, mainly for fruit or vegetables that you can store for a longer time, and you need to account for some losses during transport. You also cannot control the temperature so much, so you have to do some monitoring advisably to avoid that you have too cold temperatures, chilling injury, freezing injury, and so on, and you have to have a storage facility available. Last thing you can do is cool with naturally available ice, snow, or cold water. Speaks for itself. So if you have this available, which has been done, for example, a long time ago in the desert where you have ice houses or ice pits and so on, you can even if as I mentioned, make your own house with radiative cooling. So that's a possibility to actually cool down fruit. You can also, for example, try to cool down materials with a high specific heat capacity, stone or also water containers, and use them as cooling elements in your insulated room as well. Apart from if you don't have ice or let's say cold water from rivers available. Cold water, ice, very high thermal capacity, specific heat capacity and density, so it can contain a lot of cold energy, so it's very good for cooling. You can reach rather low temperatures, but you of course need to have them available. They're not always available in regions where you have elevated temperatures. What happened a lot with ice houses, that they produced or gathered ice and so on during the season where actually it was rather cold, and then they used it in a very well insulated enclosure to keep down the temperatures for a longer time when it was then summer, for example. Good. So what are the take-home messages? Well, you have a lot of passive cooling technologies available, some of which could serve your purpose. So it's always good to think about, in my case, my use case, where do I have cold energy closely available for me to cool down, and at which point in time, in which season. But there are many different options. What's very important is make sure, if possible, that you also monitor the performance, how much you can cool down. If you can cool down only 1 degree compared to ambient or something, or compared to the case without cooling, it will not have a big impact on your fruit or vegetables. So it depends on how low you can drop the temperatures and for how long you can drop the temperatures. This is important because if it has no impact, then of course smallholder farmers will not start using these things. If you need more info, please have a look at our cooling atlas, which I showed here. There are more details given there. Thank you. That's it.